A while ago, we have mentioned the general multiplication rule wherein we multiply if we want to find the probability of the intersection of two events. However, there are cases wherein one event does not affect the other. If we remember in our general multiplication rule, let's write it here, our general multiplication rule is that to find the probability of A and E, let's first find the probability of the first event happening, then the probability of the next event given that the first event has happened. There are cases wherein there are two events that do not affect each other's probability or number of outcomes in its sample space. Those events are said to be independent. So, let's have our definition here. An event E is said to be independent from an event A if the probability that E occurs is not influenced by whether A has or has not occurred. So in symbols, the probability of A and E happening, if they do not affect each other, will just simply be the probability of A times the probability of E. Or the other way around, we can simply write it as the probability of E times the probability of A. Anyway, the two events do not affect each other. So, let's have an example here. Let a fair coin be tossed 3 times. Let event A, the first toss is a head. B, the second toss is a head. C, exactly 2 heads are tossed in a row. We are asked which of the two events are independent. So, let's try to analyze this example here. So we know that the sample space, or the elements rather, of this set, of this event, the first toss is a head. If you toss a coin 3 times, would be, of course, when you get all heads. Then when you get 2 heads and a tail, then you get a head, a tail, and a head, and you get a head, a tail, and a tail. All first toss is a head. If the second toss is a head, then the possible outcomes would be, of course, you still have all 3 heads. And you still also have this one, head, head, tail. Then you can also have your tail, head, head, and your tail, head, tail. Event C, exactly 2 heads are tossed in a row. That would simply be if the first 2 are heads, if the last 2 are heads, or all 3 tosses are heads. So, if one does not affect the other, then we shall be able to see that relationship in their sample space and later on in their probabilities. So, the probability that A happens is 4, because there's 4 of here, out of when we toss a coin 3 times, that is actually 8, a total of 8 possible outcomes. So we have a 4 out of 8, or a 1/2 chance of getting a first toss is a head out of 3. Second toss is a head would also be 4 out of 8 chances, or 1 in 2 chances, or a half chance, or a 50% chance. Exactly 2 heads are tossed in a row would be 3 out of 8 chances. Now, according to the definition of independent events, the probability of A and E will just simply be the product of the probability of A and the probability of E. So let's see. Let's use a different color. For the probability of A and B, we have here the probability of A. Let's follow first our formula, times the probability of B rather. So there. So the probability of A and B is, we consider the intersection of events A and B, then over 8. So the intersection here would be your head, 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 and head, head, tail. There you go. So we have 2 out of 8 chances, or a 1/4 chance, that we have a first toss and the second toss is a head. If we also get 1/4 if we multiply the probability of A, which is 1/2, and the probability of B, which is also 1/2, then by definition, we can say that the two events are independent. And we know that 1/2 times 1/2 is 1/4. So therefore, by definition, the event A, first toss is ahead, and event B, second toss is ahead, are independent of each other. Which makes sense. Whenever you toss a coin, the first toss will not affect the second toss. Now, double check if B and C are independent and A and C are independent. Alright, so let's first check the definition. Let's write it here below. The probability of B and C. Better if we write it here first. Let's erase that. And let's level it up here. There you go. So, will the probability of B and C will be equal to the probability of B times the probability of C. The probability of B and C, so let's look for our intersection. We have 1 here. We have 2. So the probability of B and C would actually be... Oops, I think I forgot something here. This is supposed to be an HHH. And that is also an intersection with this here. That means we have 3 out of a total of 8. So 3 out of 8. Will that be equal to the probability of B, which is 1/2 times the probability of C, which is also 3/8? Well, obviously not. So therefore, the probability of B and C is not equal to the probability of B times the probability of C. Therefore, B and C are not independent or dependent, let's write that, are dependent events. Meaning, one event affects the other, or the outcome of one event affects the outcome of the other event. Which is true, because if your second toss is a head, it will affect that exactly 2 heads are tossed in a row. Because that second is crucial. Because if you have exactly 2 heads tossed in a row, it can either be the first or the second head, or the second and the third head. So that second toss is crucial. Hence, events B and C are dependent. How about events A and C? So let's just have it here. We have event A, or the probability of A and C is equal to the probability of A times the probability of C. So the probability of A and C, let's look for, we have here this one here. This is the one that is common, HHH. We also have HHT. There you go, and I think that's it. So this is 2 out of 8, or 1/4. Will it be equal to the probability of A, which is 1/2, times the probability of C, which is 3/8? And it's obvious that 1/4 is not equal to 3/16. Which means events A and C are also dependent. Because if exactly 2 heads are tossed, it affects the probability if the first toss is or is not a head. Hence, events A and C are also dependent, while it's only events A and B that are independent events.